Hello, everyone. Welcome to this new SimScale webinar. Thank you all for joining. Today, we will be talking about rapid design simulations for home appliances and consumer electronics. My name is Khairi Deri. I am part of the solution engineering team, application engineering team here at SimScale, and I have a background in civil engineering, computational mechanics, mostly focusing recently on computation fluid dynamics, finite elements, and electromagnetics. All right, so before we get started, I would just like to remind you that your mics are going to be muted throughout the webinar duration. If you do have any questions, please post them in the chat function in the GoToWebinar panel, and we will make sure to address those towards the end of the webinar, or if we don't have time by then, we will make sure to follow up on your questions afterwards. All right, so the agenda for today is we will start first by giving a brief SimScale introduction to those of you who might not know us already, followed by a description of what's the case that we will be discussing today. We follow that with a live demonstration so that you can get an overview of how things look like on the SimScale platform live. We summarize the results in the end, and we finish with a Q&A. Sounds good. All right. So what is SimScale, right? So I think to understand what is SimScale, let's just describe briefly what is the mission behind SimScale. So the mission behind SimScale is that we really want to empower engineers and designers and organizations on a more holistic level to really democratize simulation, to simulate more broadly, to simulate early in the design process, to make simulation something more common rather than very focused on, let's say, specialized teams that does always the expert type of thing. So that's kind of the mission of SimScale. And how we try to achieve this goal or mission is really with what I'm going to discuss at the moment. So what really makes SimScale the simulation platform that it is today? I think the major thing behind it is that SimScale is a cloud native solution, right? So which means that you can access it from anywhere in the world at any time. You don't need a VPN, you don't need a remote desktop. You can access it on the internet from the browser that you like. And as long as you have an internet connection, you are able to simulate, even from the humblest of laptops, because we do all of the heavy lifting and the infrastructure work from our side. Moreover, SimScale is one platform for lots of various different physics. These physics include flow simulations, electromagnetics, thermal, structural, and the coupling between them. There are no disconnected tools that are used in silos on the SimScale platform, and you can essentially use SimScale on various different design stages. So whether it's an early design stage or whether it's a final detailed high fidelity simulation, SimScale can help with both of those use cases. Now, as a consequence of SimScale being a cloud solution, collaboration becomes very easy. And that's mainly because everything's happening on the internet. So for example, if I would like to share a project with a colleague, whether he's sitting or she's sitting in the office next door or in a completely different continent, I can simply share a link or type their email in the share functionality on the platform, and I'll be able to share that very quickly without having to download gigabytes of data and then putting them on some cloud function to be able to share those. It's kind of a Google Docs style collaboration that we have here. Moreover, SimScale is AI powered. So next to the PDE solvers that we have here, we also enabled AI solve, so which allows you to predict the simulation results using an AI model that is trained on existing simulation data that you have collected for a long time, for example, on the simulation platform. And I think really one of the major use cases, in my opinion, for this is if you would like to explore a large design space. Sometimes that becomes infeasible if you want to do a simulation, especially when we talk about sophisticated stuff on a very large domain. It's lots of resources that needs to be done. The AI, what can help really here is that it can narrow down that design space into a smaller subset that we can then use for this high fidelity simulation. By the way, we have done lots of webinars regarding AI. So if you are interested, I'd invite you to our website, and essentially you can dive deeper into what we offer today, and we're happy to have conversation regarding that. And finally, SimScale also can be used at any scale. So whether you are purposing to use SimScale for a single simulation workflow or multiple simulation workflow, whether you want to run large design explorations or one simulation, it doesn't really matter, right? Because in practice, or basically in theory, when you are using SimScale, you have access to unlimited computing power at your fingertips, along with unlimited storage. All of that stuff is kind of covered from our side, and I'll cover these details a little bit more in the next slide. So, from the past conversations that we were having recently over the past years as well, with various different companies in lots of different sectors, essentially there is always a common point that everyone is trying to improve to kind of really enhance in their current workflows. And it all starts, for example, with meeting quality control regulations, reducing carbon emissions, figuring out ways to improve the production efficiency in the company, both on the product side of things, but also on the overall system that the company operates at. So like, it kind of all revolves on how quickly we can make products, but not just quickly and then the product would end up failing quite often, but rather quickly and robustly. That's essentially the main goal. And from those communications that we have, it's very clear that in the way that currently things are being done, when you want to incorporate simulations into the design process, usually this takes from weeks to days as a simulation lead time. And it has reasons behind it that I think that are clear to all of us. And some of these reasons is the simulation work is concentrated in an expert team. So for example, you have your simulation expert team that take requests from the designers, the product engineers that are thinking of the new ideas that they want to do, and they're sending those ideas to the simulation experts team to kind of verify, to help in reducing prototyping costs and so on. So there is always this backlog of simulation requests that the simulation expert team have essentially to deal with. In those design iterations that we kind of do, some changes are really simple and they don't always require the use of or time of a simulation expert, and those can be done by a designer. Now, if a designer needs to do these things, of course, they have to learn a sophisticated software. They need to manage the IT. There's lots of stuff that goes with it, right? And I think that's what SimScale, going back to our mission, is really trying to help in resolving in kind of in improving the overall process. And we're doing this by providing a single platform that combines everything for you. We take care of all of the infrastructure, so all of the heavy lifting. You can run simulations theoretically from your phone, right? The SimScale is, of course, optimized for a laptop, not for a phone, but in theory, because we don't require your computing power on whatever device you're using for the simulations, you can run the simulation on the browser, close the browser, you get an email later, and then you kind of, that's how the interaction is. And inside this software, the UI experience is also unified among different solvers. So whether you're using structural mechanics or electromagnetics, which is like different, quite different in terms of physics, but the UI experience is the same. And on top of that, you also get access to support functionality from SimScale. So even if you are new to simulation, or if you want to verify stuff, you can always get in touch with simulation experts, and in particular SimScale experts, live in the platform. And hopefully I'll be able to show that later as well, live as we proceed. All right, so that's a little bit about SimScale. I think now let's shift gears and start talking a little bit more technical, or at least laying the ground before we start talking a little bit technical about what is the case study that we'll be looking at today. So the case study for today is we will basically look into induction cooking, how SimScale can be used to design, analyze, the performance of an existing induction setup or of a new design process, etc. And I thought it makes sense just before we get into all of that to kind of just give a brief reminder or just a very quick overview of what induction cooking is really about. So the idea behind it is, of course, which I find personally very cool, is that it uses electromagnetic fields to directly heat the cookware. So it's unlike traditional stoves. We're not heating the cooktop surface, and then there is that kind of conduction process happening, but rather we're talking about electrical, but rather it heats the pot directly, right? And this gives us few advantages like precise, rapid temperature control. It's energy efficient, it's safe and cool, and also precise in terms of temperature adjustments and so on. The principle behind how it works is all based on electromagnetic induction. I have lots of respect for Faraday, who discovered this stuff back in the 1800s. If I remember correctly, it was the 1800s, late there. But kind of, it's a very cool thing, essentially, right? You have the changing electromagnetic field that's produced in the coil by a very rapidly changing current. We're talking here frequencies of around 20 to 30 kilohertz, or it could be, of course, higher than that, depending on the application. I've read some papers that there's like high frequency induction cooking as well that goes up to 100 kilohertz. But in this case, we'll be focusing more on a lower range, so 20 to 30 kilohertz. But circling back, essentially the principle, this changing electromagnetic field induces eddy current in the cookware. And this eddy currents, essentially, there are loops of current, which we will see as well later in the simulation. As they move inside the material, due to the resistance of the material, they generate heat losses, ohmic losses, Joule heating, whatever you want to call it. And that essentially produces heat and essentially cook a lovely steak or whatever we are wanting to enjoy on that evening, right? Now, when it comes to the design of a induction cooker, of course, there are various design questions. And I think I can talk a little bit about some design questions that I feel my knowledge would help me a little bit in talking about these. And they are more on the electromagnetic side and the thermal side. And I've chosen here a subset of questions. And on the electromagnetic design question side of things, we have essentially the coil geometry, and we want to understand how we can optimize the placement of it, how we can maximize the energy transfer from the coil to the pot of different sizes. When we talk about positioning, we also talk about what is the optimal air gap. And then when we talk about the optimal air gap, that relates as well to the frequency that we are operating in and the skin depth. And all of these things kind of interconnect with each other and kind of they form the overall electromagnetic design. Of course, there are lots of other things too, right? But at least these are the things we would focus on a little bit today. And something I didn't mention yet is also the variation of the output power on the pot depending on the material that we are using. And can we optimize the whatever we design to cover the range of what materials exist out there in the market today? And electromagnetics is one side of the equation, but of course you also get the thermal side, where you, for example, you want to understand the cooling inside the induction hub and make sure that the fan is able to produce, let's say, enough heat, convection to be able to cool the inside of the induction hub and make sure that the components are not overheating, right? And that's something SimScale can also help with. And most importantly is, of course, understanding how much time does it take for the pot to reach X temperature, or how quickly can it react to such things. And those are the stuff that we would look at a little bit as well today. All right, now before we jump into a live demonstration, I would just like to give you a very brief overview of the model specifications that I've used here for this analysis. So the operating frequency range that I worked with was between 20 to 30 kilohertz. The applied current is around 20 amps. The coil consists of an inner coil and an outer coil, both of diameter 1.7 millimeters. The inner is at 20 turns and the outer has 10 turns. In the design, of course, we also need to think about the air gap size. So here I've investigated air gap sizes between 4 to 10 millimeters. The pot material was of cast iron with a variable relative permeability, but of course that also can be extended to the conductivity, and essentially some other specifications regarding the pot that you can see here. All right, so now let's jump into the SimScale platform and take a look at how everything looks live on the workbench. What I'll be doing right now is simply switching between different tabs. As I mentioned earlier, SimScale is a cloud native solution, so everything is really happening on the internet. And right now we are inside the SimScale environment, and in particular the post processor, right? But this is the workbench. That's where you interact with your CAD model. That's where you import your CAD geometries. SimScale works, by the way, with almost all native CAD formats out there. So whether you're using Parasolid, SolidWorks, Inventor, Rhino, CATIA, etc., you can work directly, import them to SimScale and start working on that. After you import your geometry, of course, the next step is to create a simulation. SimScale offers different physics, as we mentioned earlier. So those are flow simulations, so whether it's incompressible or conjugate heat transfer, where you couple radiation, conduction, and convection all together with the humidity and all of other stuff as well, if you like. You have the structural package, and most recently, electromagnetics. And I think that's kind of the mostly the focus of today. Now, what we are visualizing at the moment is the results from an electromagnetic simulation. And what I would like to do here is understand what the ohmic loss distribution essentially looks like under the spot over here, right? So the arrows represent the eddy currents that are flowing at the bottom of the pot, and mainly in the skin depth layer inside this pot. And kind of this essentially what generates this uniform heating of the pots that we can essentially characterize and quantify to as much how much power is this output power is my electromagnetic system producing on the pot. And here, for example, you see that for this particular design, we have around 2 kilowatts of energy generated on this. Now, this was for 30 kilohertz at 200 relative magnetic permeability, but I can, of course, extend this to cover a wider range of design scenarios. And you can visualize here, of course, the flux densities, the electric current densities, and so on, and calculate the losses from the ferrites as well, if you like. But moreover, you also get some access to other results, like, for example, the inductance matrix of your coils, the impedances, the leakage inductance, the induced voltages, and so on. What would be cool is to kind of define the pot as well also as a coil, for example, at 0 voltage, and then kind of understand how the impedance of the pot acting as a third coil matches with the impedances of the existing supplying coils, and kind of just to get more insight into the impedance matching side of things. But cool. Now, we have here a simulation that's already set up and so on, but let's take a step back and maybe in 2 minutes just see how we can start this simulation setup process and really take it from there. So what I'll do is I'll go to Google, just to my browser of preference, and I'll navigate to SimScale. And then from SimScale to the website, I log into my account via username and a password. And from there, I can navigate to my dashboard. Now, inside the dashboard, that's the place where you get a data management system kind of for free with the SimScale platform, really. And you can store all of your simulation data here, organize it in folders, in various different spaces for different subsystems inside the team, for example, and essentially manage all of your data here. You have practically, by the way, unlimited storage capacity on our cloud service. What I'll do is I'll go ahead and create a new project. Let's call it induction heating, electromagnetics, or multiple physics, and create project. So now we have an empty template that I need to start filling, importing my geometries, and doing the simulation setup from there. But that's not what I will do. What I will do instead is I will import an existing template from the simulation that I have already done. And you can think of this as something that can be useful. Let's say if you have a simulation expert in your company that created a template for designers to start doing some quick changes on their design, or for example, let's say you have worked on something similar in the past and you want something to start with, not from an empty place in terms of materials, and setup, and so on, then you can use this import function. And what it would do is it will import your geometry and the existing simulation setup of that material, right? Of course, you can go ahead, define a BH curve, for example, for some of the materials that you have, decide what's the frequency that you want to simulate on, and click run, right? Now, because SimScale is cloud native, you can really run lots of simulations at the same time in parallel. So I can go ahead, for example, and check what would be the results at a different frequency range and click run. I can go, for example, and change the relative magnetic permeability at a particular frequency and click run again. And practically, you really have no limits on how many simulations you can run in parallel here. But now we ran the electromagnetic simulations. Now I want to use those results and start a thermal simulation. So I'll do exactly the same thing. I'll go there, I'll click on my template, and I'll choose the template that I've created for my transient thermal simulation. I'll click on import. So what I have here is now a thermal simulation using the conjugate heat transfer solver, where I'm interested essentially in understanding how does the temperature evolves with time. So here I have a power source applied on the pots, and I can go ahead essentially now and run a thermal simulation as well. And I can, of course, investigate various different output powers on the pots and kind of understand how the temperature changes under different operating conditions. In this case, I'm simulating this for 4 minutes, but I can, of course, adjust that as I like. Cool. Now, that's a little bit on the simulations and those kind of aspects. If you do have more like detailed questions, feel free to post them in the chat, or feel free to get in touch with us as well after the webinar. I would be very happy to give you a live demonstration, a little bit more in detail, a little bit more technical, and then we can kind of take it from there. I really wanted to purpose this as a little bit of a high-level overview of what you can do or what is possible inside SimScale, right? And yeah, as I promised, I wanted to show the chat functionality here. So if you are a new user to SimScale or even an experienced user and you have any particular question that you would like to ask us, get help on, then you can use the chat functionality to get in touch with us. And the goal behind this is that we try our best to make sure that you get what you need from your simulations, right? And here on the top panel, you can also share projects with different colleagues, define what access you would like to give them, whether is it copy or view. Sounds good. All right. So now let's switch gears again. Let's go back to the slides and summarize the results and go to the Q&A session. So, few things to cover here in a more detailed analysis on the results, right? So, let's focus on the left-hand side of the screen. So I have here two plots mainly comparing how the output power changes versus the relative permeability and the air gap. So the x-axis is the permeability, the y-axis is the ohmic losses, and the different colors represent different air gaps here. And what we clearly see is that with decreasing air gap for the same frequency, and that's a keyword here, we do essentially, of course, get more output energy on the pot. That's also can be seen as we change the frequency range from 20 kilohertz to 30 kilohertz. Of course, we can have more data points here. And we see with the, for this particular air gap, the more we increase the frequency, because the rate of the flux essentially is increasing, so we get more induction effects happening, and that's kind of resulting in more ohmic losses. But we need to pay attention to how those changes are affecting the skin depth, because then the equation can start get a little bit more interesting there. On the right-hand side, we have a comparison between two different designs. So the induction coil itself has also ferrite elements in it. And we have the version 1, which have the standard kind of ferrite orientation, 6 bars. And on the other one, we have other smaller 5 bars kind of supporting the other ones. And the goal behind this kind of to improve the efficiency of the induction cooker or the energy of the flux. And that's kind of really what we see over here. So with the addition of the ferrite bars for different air gaps, we do get the red color higher power energy in comparison to the ferrite bars, and we can quantify those quite in detail. Now, shifting gear to this very briefly, we can take a deeper look on what is happening on the field due to these changes. Here I have two cases that I'm looking into, the 4 millimeters and the 8 millimeters gap case for the two different designs. And if I would like to pay your attention to just one element here, we can take a look at the electric current density of the 8 mm gap and compare it to the counter one of the standard design. In this one, we see a more uniform distribution of the current density in comparison to the first version, and that, of course, results to a more uniform ohmic loss distribution on this particular object, and kind of resulted here of around 180 watts of additional energy that we can produce for the same air gap, for the same frequency and coil design. Now, what happens to the ferrite bars themselves under the same operating conditions is kind of what we see here on the left-hand side. So with the addition of more bars, we kind of are reducing the potential of saturation in the particular induction coil itself. And here we can also, of course, get insight to how the flux density varies with the change of the air gap and so on. But cool, all of those stuff were regarding the magnetics. I'll finalize everything now with just a quick insight on the temperature side of things. So here I have two different simulations. On the left-hand side, one load case, a 4 mm gap between the coil and the pot. Here we see the output power generated on both, again for the 8 mm gap. And what was interesting for me to see here is after 5 minutes or after 4 minutes, the temperature reached around 680 Celsius degrees on the small pot for the 4 mm gap and 513 Celsius degrees at the 8 mm gap. And of course, this is quite high. But what kind of this tells us is we really don't need to operate this at the maximum energy that we can generate. So there would be some kind of limiting factors that we can apply to control the amount of energy, or maybe a function that allows the user to reach a particular temperature at a very rapid time, right? So that's kind of some of the insights that we get from here, right? And if we want to take this even one step further, we can run a thermal simulation on the induction hub itself, varying different air vents designs. So for example, here we have an air vent on the front or air vents on the sides. Of course, what I have over here, especially for the induction hub, or basically mainly on the induction hub, is kind of a slightly simplified model. But really, I want here to give you the idea because you guys are the experts in this field or in the design of your appliances, right? Bring in your CAD models to our platform, run those simulations, test it for yourself, and let us know what you think and how we can help in those aspects. All right, I think that's mainly it what I wanted to cover today. I hope you found it insightful. I hope it gives you an idea of what SimScale is really about and how we can help in the design processes in general. If you do have any questions, please let us know. And yeah,
Hi, it's Nagwan here.
hi Nagman.
Larry, fantastic presentation. Thank you so much. We do have some questions coming in from the attendees. So should we take a couple of quick ones now?
Yeah, absolutely.
Fantastic. Larry, we have an attendee asking that EM is a relatively recent solver in SimScale, correct?
That
Compared
is
to the
correct.
others. Anyway,
That is
yeah. So
correct.
where can they find some information on validation and references and a bit more about what's been applied in the solvers in SimScale?
Yeah, absolutely. So that's a question we get quite a lot. So what we decided, or basically SimScale became quite experienced in flow, structural, and thermal applications in the past 10 years. And we see a large demand for electromagnetic simulations in the cloud in the market. So what we did, we decided to pair with or collaborate with a company called EMWorks. And essentially the electromagnetic solver that we are providing is based on their technology. And they are a Canadian-based company that had been doing electromagnetic simulations for the past 25 to 30 years. And they are very established in this market, and they have countless validations and use cases on their website as well. If you are interested, please get in touch with me after the webinar, and I can kind of give you more information regarding these things as well.
Nice, nice, absolutely. And Kari, another question is, we used to CFD solvers, we used to FEA structural analysis. When it comes to EM, what are the interesting things you've observed around meshing and simulation runtimes, computational times? How does it compare to the CFD thermal solvers we're used to?
Well, I mean, of course, it varies, right? So in electromagnetics, I think the main aspect when it comes to meshing really applies the same to finite elements and CFD, which is if you expect a large change of a field result, whether that is the current, or is that the ohmic loss, or the flux density, or for example, velocity in CFD, right? In those locations, you need to have kind of the same mesh criteria, the same mesh best practices being applied over there. Electromagnetic simulations in general supposedly should be a little bit faster, but of course it also depends on the type of physics that you are solving. So if you are like coupling different physics, or if you're running transient, then of course the electromagnetic simulation can also take some time in comparison to the other. But this is really depends quite a lot on the actual use case that you are solving, on your mesh time, and those kind of things. To give a reference, the electromagnetic simulation that I ran on this induction cooker took around 100 minutes, I think, for a relatively finer mesh for around, I think it was 2 millions, something I would need to double check. On a relatively small machine size, right? The SimScale, you have access to 192 cores. So if you want a faster computation, you can choose a larger machine and enable a faster computation time. But you should always remember that
Yeah,
you can run those simulations in parallel as well. So if
yeah.
you have one
See, this is
simulation that
really
takes 60
interesting
minutes,
detail.
all of them take 60 minutes.
Absolutely. This is really the value proposition at SimScale. Harry, we have a couple of attendees asking, there was a AI webinar yesterday
Correct.
by our colleague Ajit, and it was on CFD for valves, okay? And we've
Hmm.
shown various other AI simulation demo projects for things like pumps and bellows, exhaust manifolds. When is AI coming to the email solver? Or
I
when's
hope
the soonest you think? Yeah, go on.
that's a good question. I would love for it to be available tomorrow. I have lots of ideas that I would like to test.
Yeah,
But I hope in the next few months. I mean, it's something that we are still like working on. We're expanding now on where it's mostly demanded from our existing customer base, and that's really, as Nagman just mentioned, on the structural and CFD side of things. 100% it will come to electromagnetics as well, hopefully sometime in early 2025.
fantastic. We look forward to that. Um, Kari, we have another user question, and
Yeah.
that's, on the coupling that you showed earlier between EM and thermal, what kind of computation times did that take?
So for the coupling that I've done over there, that was is a weak coupling. So when we talk about strong coupling and weak coupling, the strong coupling, which means that the electromagnetic equation is being solved in parallel with the, not in parallel, but kind of we solve the electromagnetic problem, and then we take the outputs, put in the thermal, and this pattern repeats until we reach some kind of a convergence criteria. What I've shown you today is that I've ran the electromagnetic simulation independently, and I've took the results and I've put it into a thermal solver on SimScale and essentially ran this. The thermal simulation was quite quick. It was maybe, I think, 40 minutes conduction problem with convective boundary conditions and so on. We are working at the moment on enabling transient thermal coupling with magnetic, and that should be available hopefully sometime as well in 2025, hopefully in the early days of 2025, where you can have stroke coupling between the two. The the cool thing is though with the thermal problem, you can define temperature dependent properties. So that's something I got asked before by a customer that we have, is the thermal conductivity of the cookware changes quite a bit for such high temperature ranges that we are dealing with. And that's something that, of course, you should and can take care of in the thermal problem. Um, yes, I hope this kind of answers that question. But if there is a follow-up from the attendee essentially who asked this, please get in touch with us. I'll be happy to dive in more detail. Kind of to understand as well, what is your simulation requirement kind of to the application that you have.
Exactly, absolutely. Okay, Harry, last question from my side then. For anyone new to
Hmm.
SimScale who's on this webinar, what's the easiest and best way to get started, to jump straight in with some of the sample projects or other projects you've shown? And if you can answer that, and I'll hand over to you to make some closing remarks. Thank you.
Yeah, absolutely. I mean, I think the best way to go about that is just go to the SimScale website, go to Google, type in simscale.com, And once you're there, essentially, you can interact with our create an account. You would be access to the community version, and you can start playing around, testing, getting a feeling for it. You can try some of our tutorials. And then if you have more questions or essentially a more sophisticated case that you want support on, get in touch with us, and we would be very happy to help you with that. So I think really the simple answer, just go to the SimScale website, and I'm sure you'll find your way there. Um, on how like to run those simulations directly on the cloud and see it for yourself as well. Cool. Sounds good. All right, then. Thank you all again for joining the webinar, and we'll be looking forward to seeing you as well in our future webinars. Again, if you have any questions, get in touch with us afterwards, and we would be happy to assist you with your simulation needs. Thank you again, and take care. Ciao, ciao.